Now, in this lecture, we'll answer on two questions. In the first question, we will find out the length of line segment X. In the second question, we'll find out the value of the shaded area that is inside the quarter circle. So we'll start with the first question. In the drawing, we have triangle ABC. Note that angle ABC equals to 30 degrees. Angle ACB, this angle also equals to 30 degrees. Angle DAE, this angle equals to 60 degrees. And we also know that line segment BD equals to 5 units, line segment EC equals to 4 units, and our mission is to find out the value, the length of line segment DE that is equal to X. Okay, so first of all we focus on triangle ABC. In triangle ABC, those two angles are equal to each other. So I write it down. So angle ABC, this angle, is equal to this angle that is actually angle ACB, and both angles they are equal to 30 degrees. I repeat again, in triangle ABC, we know that angle ABC equals to angle ACB, and they are both equal to 30 degrees. Therefore they are equal to each other. And according to the rule that in front of equal angles in the triangle there are equal sides, we get that in front of this angle we have side AC, in front of this angle we have side AB. So side AB must be equal to side AC. Okay, AB equals to AC. Okay, so we can write here that side AB equals to side AC. In the next step, we define angle BAD, this angle as alpha. We define angle EAC, this angle as beta. And we know that the sum of the angles in any triangle is equal to 180 degrees. So here, and especially the sum of the angles in triangle ABC must be equal to 180 degrees. So which angles we have in triangle, inside triangle ABC, we have one angle that is equal to 30 degrees, plus this angle is also equal to 30 degrees, plus this angle that is equal to alpha, plus this angle that is equal to 60 degrees, plus this angle that is equal to beta. In total, the sum of those four all angles, they must be equal to 180 degrees. Okay. The sum of the angles in triangle ABC equals to 180 degrees. So here, 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. And here, in this side of the equation, plus alpha plus beta. In total, this side of the equation equals to 180 degrees. So here we will subtract 120 degrees from this equation, and we get that alpha plus beta equals to 60 degrees. Okay, alpha plus beta equals to 60 degrees. In the next step, we'll do two constructions. In the first construction, from point A, we draw a straight line in such a way that the angle between the straight line and side AC will be equal to alpha. So this is the straight line. So we drew this straight line in such a way that the angle between this straight line and side AC equals to alpha. So this angle equals to alpha. And we will do another construction from point C. We will draw a straight line in such a way that the angle between the straight line and side AC will be equal to 30 degrees. So the angle between the straight line and side AC equals to 30 degrees. This angle equals to 30 degrees. And then we will extend the two straight lines until they intersect with each other. And we define the intersection point between the two straight lines as point F. So actually, by the constructions, we created here triangle AFC. In the next step, we will prove the triangle AFC, this triangle is congruent to this triangle ABD. So I write it down. We will actually prove that triangle ABD is congruent to triangle AFC. So why those two triangles congruent to each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. So we can write down that angle BAD, this angle, equals to this angle, that is actually angle CAF, and they're both equal to alpha, therefore they are equal to each other. In addition, we have already proved that side AB equals to side AC. And finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So angle ABD, this angle, is equal to this angle, that is actually angle ACF. and both angles they are equal to 30 degrees, therefore they are equal to each other. So we actually proved that triangle ABD is congruent, this is the sign of congruent, to triangle AFC according to angle side angle rule. Okay. Those two triangles can go into each other according to angle side angle rule. I will explain what I mean. Actually, side AB and those two angles that attach to it that are alpha and 30 degrees in triangle ABD are correspondingly congruent to side AC and the two angles that are attached to it that are alpha and 30 degrees in triangle ACF. Therefore, those two triangles can go into each other according to angle side angle rule. Okay? And from the fact that those two triangles can go into each other, we conclude two things. The first thing that we will conclude that side BD equals to side FC. Side BD equals to side FC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say BD and FC, must be also equal to each other. But according to what is given in the question, BD equals to 5 units. So we can write here that BD equals to 5 units. And from this equation, 5 equals to BD equals to FC, we derive that FC is also equals to 5 units. FC equals to 5 units. So I can write here that FC equals to 5 units. And the second thing that we will prove from the fact that, the second thing that we will conclude from the fact that those two triangles can go into each other is that side AD equals to side AF. AD equals to AF. Okay? According to the same rule that corresponding sides in congruent triangles are equal to each other. And if we define side AD as A, here side AD equals to A. So here side AD equals to A according to our definition. Then from this equation A equals to AD equals to AF, we conclude that AF is also equals to A. AF is also equals to A. Side AF is also equals to A. In the next step, we'll join points E and F together by a straight line. And we'll prove that the green triangle ADE is congruent to the orange triangle, triangle AEF. We prove that the green triangle is congruent to the orange triangle. We have already found out that alpha plus beta equals to 60 degrees. So here angle EAF equals to alpha plus beta, therefore it is equal to 60 degrees. So why those two triangles can go into each other? So I write it down, triangle ADE So first of all, we just right now proved that side AD equals to side AF, and that is equal to A. AD equals to AF equals to A. AD equals to AF equals to A. In addition, those two angles, they are both equals to 60 degrees, therefore they are equal to each other. So here we can write down that angle DAE, this angle equals to angle EAF, this angle and both angles they are equal to 60 degrees. And finally, side AE is a common side that belongs to both triangles, so side AE equals to itself. It's a common side. So here, side AE equals to side AE. It's a common side. That belongs to both triangles. So we actually proved that the green triangle ADE is congruent. This is the sign of congruent to the orange triangle AEF. According to angle side angle rule. I will explain what I mean. We actually proved that the green triangle can go into the orange triangle according to angle side angle rule. Side rule. Here it is according to side angle side rule. We actually proved that those two sides and the angle that is included between those two sides in the green triangle can go in correspondingly to those two sides and the angle that is included between those two sides in the orange triangle. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we conclude that side DE equals to side EF. Side DE equals to side EF. Okay? Side DE equals to side EF. Again, side DE equals to side EF according to the sum rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the corresponding sides, that is to say DE and EF, will be equal to each other. But according to what is given in the question, DE equals to X. DE equals to X, so from this equation X equals to DE equals to EF, we conclude that EF is also equals to X. EF is also equals to X. Okay, here EF equals to X. In the next step, I will present to you the law of cosines, and we will implement the law of cosines in this triangle, triangle EFC. So, what is the law of cosines? The law of cosines is true in any triangle. So we can write here that in any triangle, so if we have triangle ABC, that could be any triangle. This is triangle ABC. Side AB equals to A units in its length. Side AC equals to B units in its length. And the angle between side AB and side AC is theta. And side BC equals to C units in its length. Then in triangle ABC that could be any triangle, the following equation is true. That C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I'll repeat again. In the right triangle, triangle ABC, according to the law of cosines, we get that A squared plus that C squared, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. So we will implement the law of cosines in triangle EFC. So I will copy the I will copy triangle EFC in this page, and we will implement the law of cosines in triangle EFC. Here, angle ECF, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees. Side FC equals to 5 units. Side EC equals to 4 units. And side EF equals to X. So, this is triangle EFC that I copied from the original drawing. So So according to the law of cosines, so if we implement the law of cosines in triangle EFC, we get that according to the law of cosines, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Repeat again, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. So here x squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40, times cosine 60 degrees. Cosine 60 degrees equals to 1/2, so let's substitute cosine 60 degrees by 1/2, and we'll get that x squared equals to 16 plus 25 is 41, minus 40 over 2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20. 41 minus 20 is 21. So we found out that x squared equals to 21. So here we take a root out of this equation and we get that x equals to the positive root of square root of 21, because of the fact that x is a left, it must be a positive number, therefore we take only the positive root of square root of 21, or in terms of numbers it is equal to 4.58 units. Okay. I'll repeat again. We found out that the length that we are looking for, this is the length of line segment DE, it is equal to either the positive square root of 21, or in terms of numbers, it is equal to 4.58 units. Okay. So we finished with the first question. In the next step, I will present to you the second question. So, in the drawing, we have a quarter circle. Inside this quarter circle, we have a circle with radius that is equal to 2 units. And we also have a semicircle with the same radius. The radius of the semicircle is also equal to 2 units. The semicircle and the circle are tangent to each other at this point. And here, this circle is tangent to the quarter circle at this point. And our mission is to find out the value of the shaded area. So first of all, because of the fact that this is a quarter circle, it means that this point is the center of the quarter circle. So we'll define this point as point O, and point O is the center of the quarter circle, Okay, point O is the center of the quarter circle. And we also know that this angle equals to 90 degrees. This angle equals to 90 degrees, and also, so if we define this point as point A, and we'll define this point as point B, then we also know that BO and also AO are the radii of the quarter circle. It's true in any quarter circle, okay? So here we'll define the point of tendency of tangent AO with this circle as point M. So point M is the point of tangency of tangent AO with this circle. Okay. We define the center of this circle as P. Point P is the center of this circle. And we have here rule number 1 that states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have tangent AB that is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. And we have the radius OM that is drawn to the point of tendency. Therefore, tangent AB, whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MA. So if AB is perpendicular to MA, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. So we actually can implement rule number 1 in our drawing. Why? Because in our drawing we have, first of all, point P is the center of the circle. Point M is the point of the circle itself. Therefore, PM is the radius of this semicircle that is equal to 2 units. So here we have the radius PM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent OA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OA will be perpendicular to the radius PM. So if OA is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay? So those two angles, they are both right angles, they are equal to 90 degrees, according to rule number 1. Okay? So we have here two angles that are both equal to 90 degrees. In the next step, from the center of this circle that is point P, we'll draw perpendicular on BO. Okay? So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And we'll define the touching point of the perpendicular from point P and BO as N. Okay, point N is the point of here. Point so we define the perpendicular from point P and BO as N. So here inside quadrilateral PNOM we have 1, 2, 3 right angles. Okay, I repeat again, inside quadrilateral NPOM we have 1, 2, 3 right angles. So I write it down. And the sum of right angles is 90 times 3 is 270 degrees plus the size of the fourth angle that is actually angle NPM, this angle. In total, the sum of those four angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So here we subtract 270 degrees from this equation, and we get that the missing angle NPM, is equal to 360 degrees minus 270 degrees is 90 degrees. So we found out that the missing angle is a right angle. Okay, angle NPM equals to 90 degrees. So we actually found out that all the angles inside quadrilateral NPOM are right angles. And any quadrilateral that has four right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral NPOM as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NPOM, side PM must be equal to side NO. PM equals to NO. Okay. But we know that PM equals to 2 units. It is the radius of the circle. So we can write here that PM equals to 2. And from this equation, 2 equals to PM equals to NO. We will derive that NO is also equals to 2 units. So here, NO or ON equals to 2 units. Likewise, according to the same rule, that the opposite sides of a rectangle are equal to each other, we get here that side NP must be equal to side OM. NP equals to OM. According to the rule that the opposite sides of a rectangle are equal to each other. So if we define NP as X, here NP equals to x according to our definition. From this equation, x equals to NP equals to OM, we conclude that OM is also equals to x. Okay, OM is also equals to x. In the next step, we focus on this point. This point is the touching point or the point of tendency of the semicircle, of the circle and the quarter circle. So we will define the touching point of the circle and the quarter circle as point K. So here we have an internal notch between the circle and the quarter circle, that is to say, the circle and the quarter circle are touching each other internally at point K. Okay? So it is the touching point of the circle and the quarter circle. And whenever you have an internal notch between two circular shapes, then the straight line that joins their centers together must pass through the touching point. In this case, it is point K. Okay? Here, point O is the center of the quarter circle. Point P is the center of this circle. And the straight line that joins their centers together is PO or OP. According to the rule that I mentioned, this straight line OP must pass for point K, that is actually the touching point between the circle and the quarter circle. So here, so the straight line OP must pass for point K. So you can actually write down that OPK is one straight line. Line segment OPK is one straight line. Repeat again. We found that line segment OPK is one straight line. So if OPK is a straight line, then OK is also a straight line. So I can write here that OK is a straight line. So we know that OK is a straight line. Point O is the center of the quarter circle. Point K is a point on the quarter itself. This is exactly the definition of a radius. So OK is the radius of the quarter circle. So you can write down that OK is the radius of the quarter circle. So we will define the radius of the quarter circle as capital R. So therefore OK equals to capital R. Okay. Here point P is the center of the circle. Point K is the point on the circle itself. So pk is the radius of this circle that is equal to 2 units. Okay, so in conclusion, we found out that here pk equals to 2 units, and OK, it is the radius of the quarter circle that is equal to capital R according to our definition. And what is the value of line segment OP? It is very easy to see from the drawing that the value, the length of line segment OP is equal to OK minus PK. OK minus PK. Again, the value of line segment OP equals to OK minus PK. So OP equals to OK, that is the radius of the quarter circle that is equal to capital R, minus PK, that is equal to 2 units, it is the radius of the circle. So in conclusion, we found out that the length of line segment OP is capital R minus 2. So we can write here that OP equals to capital R minus 2 In the next step, we will implement the Pythagoras theorem on the right triangle, triangle OPN. So I copy the right triangle OPN in this page and we will implement the Pythagoras theorem on this triangle, triangle OPN. Okay. Side OM equals to X, side PM equals to 2 units, and we just right now found out that the hypotenuse OP equals to capital R minus 2. So in the right triangle, triangle OPM, here by PT is the abbreviation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OP, so the square of the hypotenuse is OP squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to OM squared plus PM squared. The hypotenuse OP equals to capital R minus 2, so therefore OP square is capital R minus 2 squared. And it is equal to OM square. OM is X, so OM square is X squared plus PM square. PM is 2, so PM square is 2 squared, that is 4. So in conclusion, we found out that according to Pythagoras theorem in the question number 1, R minus 2 square equals to X square plus 4. So here we'll open the brackets on this side of equation number 1 and we get that r minus 2 squared equals to r squared plus 2 squared, that is 4, minus 2 times r minus 2 times r times 2, that is minus 4r, and it is equals to x squared plus 4. So here we have 4 on both sides of the equation, so 4 will get cancelled. So in conclusion, we found out that according to equation number 1, x squared equals to r squared minus 4r. Okay. In the next step, we'll focus at this point, that is the point of tendency or the touching point between the circle and the semicircle. So we'll define the touching point as point T. The touching point, we define the touching point between this circle and the semicircle as point T. So actually the semicircle and the circle are touching each other externally at point P, at point T. Point T is the touching point of the point of tendency of this circle in this semicircle. And whenever you have an external lunge between two circular shapes, then the straight line that joins their centers together must pass through the touching point of the two circular shapes. So if we define the center of this semicircle as point L, then according to the rule that I mentioned, point L is the center of the semicircle, point P is the center of the circle, and the straight line that joins their centers together is the straight line LP, and according to the rule that I mentioned, the straight line LP must pass from point T, that is the touching point of the two circular shapes. So here the straight line LP must pass through point T, that is the touching point of the circle and the semicircle. Or in other words, we can say that points L, T, and P, they are all located on the same straight line, or we can also say that LTP is one straight line. So we can write down that line segment LTP is one straight line. Okay, so line segment LTP, this 9 segment is a straight line. So if LTP is a straight line, LP is a straight line. So you can write down that 9 segment LP is a straight line. So here point L is the center of the semicircle. Point T is the point of the semicircle itself. Therefore LT is the radius of the semicircle that is equal to 2 units according to what is given as the question. Likewise here point P is the center of the circle. Point T is the point of the circle itself. Therefore PT is the radius of this circle that is also equal to 2 units according to what is given as the question. So the length of the straight line LP equals to LT plus TP. LT plus TP. So the length of the straight line LP equals to LT, that is 2 units, plus TP, that is also 2 units. So in conclusion, we found out that LP equals to 2 plus 2, that is 4. LP equals to 4 units. In the next step, we'll find out the length of line segment LN. But first of all, here point L is the center of the semicircle, point B is the point on the semicircle itself, therefore LB is the radius of this semicircle that is equal to 2 units, according to what is given as the question. So what is the length of line segment LN? The length of line segment LN, it is very easy to see from the drawing that LN equals to BO, that is the radius of the quarter circle, BO minus BL minus NO. Repeat again, LN equals to BO minus BL minus NO. So the length of line segment LN is equal to BO. BO is the radius of the quarter circle that is equal to capital R according to our definition, minus BL. BL equals to 2, so it is minus 2, minus NO. NO also equals to 2, so it is also minus 2. So in conclusion, we found out that LN equals to R minus 2 minus 2. Minus 2 minus 2 is minus 4. So in conclusion, we found out that LN equals to capital R minus 4. So we can write down here that LN equals to capital R minus 4. In the next step, I'll copy the right triangle L and P in a new page, and we'll implement the Pythagoras theorem on the right triangle, triangle L and P. Why it is the right triangle? Because this angle L and P equals to 90 degrees according to our construction. Okay. NP equals to X. We've already found out that the hypotenuse LP equals to 2 plus 2, that is 4. And we just right now found out that line segment LN equals to capital R minus 4. So we'll implement the Pythagoras theorem on this triangle, right triangle, triangle LNP. So here by PT is a relation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is LP, therefore the square of the hypotenuse is LP square. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to Ln square plus Np square. And repeat again, according to the Pythagoras theorem in the right triangle, triangle NP, in the right triangle, triangle LNP, LP square equals to Ln square plus Np square. So here, LP equals to 4, so LP square is 4 squared, that is 16. That is equal to Ln square. Ln equals to capital R minus 4, therefore Ln square equals to capital R minus 4 square plus Np square. Np equals to x, so Np square equals to x squared. So in conclusion, we found out that according to the Pythagoras theorem and equation number 2, 16 equals to capital R minus 4. Again, 16 equals to capital R minus 4 square plus x square. So here we'll open the brackets on this side of equation number 2 and we get that according to equation number 2, 16 equals to capital R minus 4 square equals to R square plus 4 squared, that is 16, minus 2 times R times 4 is minus 8R plus x squared. So here we have 16 on both sides of equation number 2, so 16 will get cancelled. So what left of equation number 2 after we cancelled 16? On this side of the equation we have 0, nothing left. That is equal to R square minus 8R plus x squared. So here we will add 8R to this equation, equation number 2, and we get that according to equation number 2, 8R equals to R square plus x squared. Here we subtract R square from this equation, equation number 2, and we get that according to equation number 2, eight R minus R square equals to x squared. Okay, so according to equation number 2, we found out that x squared equals to 8R minus R squared, while according to equation number 1, we have already found out that x squared equals to R squared minus 4R. So we have two different expressions for x squared. In the next step, we'll create equation number 3 that states that x squared according to equation number 1 must be equal to x squared according to equation number 2. Here x squared according to equation number 1 must be equal to x squared according to equation number 2. So according to equation number 3, x squared according to equation number 1, it is r squared minus 4r, and it must be equal to x squared according to equation number 2, that is actually equals to 8r minus r squared. So in conclusion, we found out that according to equation number 3, r squared minus 4r equals to 8r minus r squared. Here we will add r squared to this equation, equation number 3, and we get that according to equation number 3, r squared plus r squared is 2r squared minus 4r equals to 8r. Here we will add 4r to this equation, equation number 3, and we get that according to equation number 3, two r squared equals to 8r plus 4r is 12r. So we found out that 2r squared equals to 12r. So here we will divide equation number 3 by 2, and we get that according to equation number 3, 2r squared over 2 is r squared, that is equals to 12r over 2 is 6r. So in conclusion, we found out that according to equation number 3, r squared equals to 6r. Here we'll subtract 6r from this equation, equation number 3, and we'll find out that according to equation number 3, r squared minus 6r equals to 0. So here we'll take r as a common factor from this equation, equation number 3, and we'll get that according to equation number 3. So we took r as a common factor of those two expressions. So what is left from r squared after we took from it r as a common factor? What is left? It is actually r. And what is left from minus 6r after we took from it r as a common factor? What is left? It is actually minus 6. So in conclusion, we found out that according to equation number 3, r times r minus 6 equals to 0. So here we have two solutions that are possible for r. The first solution for r is, for capital R, is that capital R equals to 0. But because of the fact that capital R, according to our definition, is the radius of this quarter circle, it must be a positive number. It can never be equal to 0. So we cancel this solution. So we left only with the second solution, that r minus 6 equals to 0. We will add 6 to this equation, and we will get that r equals to 6. R equals to 6. So we actually found out that the radius of this quarter circle, capital R, equals to 6 units. Now it is very easy to find out the area of the quarter circle. It will be equal to pi r squared, that is the area of the entire circle. And if we divide the area of the circle by 4, we get the area of this quarter circle. That is to say, in conclusion, the area of this quarter circle will be equal to pi r squared over 4 when r equals to 6 units. And what is the area of what is the value of the shaded area? What is the value of the shaded area? From the drawing, it is very easy to see that the value of the shaded area it will be equal to the area of the quarter circle minus the area of the circle minus the area of the semicircle. So I repeat again, the value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. Okay? I'll repeat again, the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. So it is actually equals to the shaded area equals to the area of the quarter circle, and we know that the area of the quarter circle equals to pi r squared over 4. It is the area of the circle over 4 minus the area of the circle, that is pi r squared, and r equals to 2, so it is pi 2 squared minus the area of the semicircle, that is equal to the area of the circle over 2. And r equals to 2, so and the area of the circle is pi 2 squared, and then we'll divide it by 2, we'll get the area of the semicircle. So we know that the radius of the quarter circle equals to 4, so capital R equals to the radius of the quarter circle equals to 6, so capital R equals to 6. Therefore, capital R squared is 6 squared, that is 36. So here we have in the denominator 36 pi, in the denominator we have 4. Okay, so the area of the quarter circle equals to 36 pi over 4 square units minus the area of the circle, that is equal to 2 pi 2 square times pi. 2 square is 4, and 4 times pi is 4 pi. So in conclusion, the area of the circle equals to 4 pi minus the area of the semicircle, that is equals to 2 square is 4, and 4 over 2 is 2. In conclusion, this expression equals in total to 2 pi. And here we have 36 over 4 is 9, so in total this expression equals to 9 pi, that is actually the area of the quarter circle, minus 4 pi minus 2 pi. So in conclusion, we found out that the shaded area equals to 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So we actually found out that the value of the shaded area it is equal to either 3 pi square units, so in terms of numbers it is equal to 9.42 square units. I repeat again, the value of this shaded area it is equal to either 3 pi square units, or in terms of numbers it is equal to 9.42 square units. Okay, we finished with the second question. In the next step I'll summarize the lecture. Okay, we start with the first question. In the drawing we have triangle ABC. Angle ABC equals to 30 degrees. Angle ACB also equals to 30 degrees. This angle DAE equals to 60 degrees. Line segment BD equals to 5 units. Line segment EC equals to 4 units. And our mission is to find out the length of line segment DE that is equal to x. Okay, so we'll focus on triangle ABC. In triangle ABC we have those two angles that are equal to each other, they are both equal to 30 degrees. So here in triangle ABC, angle ABC equals to angle ACB, and they are both equal to 30 degrees, therefore they are equal to each other. Okay, and according to the rule that in front of equal angles in the triangle there are equal sides, we get that in front of those two equal angles, we have in triangle ABC we have equal sides. In front of this angle we have side AC, in front of this angle we have side AB, and according to the rule that I mentioned, AB must be equal to AC. Okay, so AB equals to AC. Okay. Then we defined angle BAD as alpha and angle EAC is beta, and we know that the sum of the angles in triangle ABC must be equal to 180 degrees. So which angles we have in triangle ABC? We have this angle that is equal to 30 degrees, plus this angle that is also equal to 30 degrees, plus this angle that is equal to alpha, plus this angle that is equal to 60 degrees, plus this angle that is equal to beta. In total, the sum of those angles must be equal to 180 degrees. Okay? So here, 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. So in conclusion, we found out that 120 degrees plus alpha plus beta equals to 180 degrees. Here we subtracted 120 degrees from this equation, and we found out that alpha plus beta equals to 180 degrees minus 120 degrees, it is 60 degrees. Okay, so alpha plus beta equals to 60 degrees. Then we did a construction from point A we draw a straight line in such a way that the angle between the straight line and side AC will be equal to alpha. So this angle equals to alpha according to our construction. Then we did another construction from point C. We draw a straight line in such a way that the angle between the straight line and side AC will be equal to 30 degrees. Again, this angle equals to 30 degrees according to our construction. Then we extended the two straight lines until they intersect with each other at point F. Point F is the intersection point of the two straight lines. Then we proved that triangle AFC is congruent to triangle ABD. Why those two triangles can go into each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. In addition, side AB equals to side AC. We have already proved that those two sides are equal to each other. And finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So we actually proved that those two triangles can go into each other according to angle side angle rule. Okay, triangle ADE can go into triangle AEF. Here, actually, you have this triangle ABD. This triangle can go into triangle AFC. Can go into triangle AFC according to angle side angle rule. Here, those two angles and side AB can go in correspondingly to those two angles and side AC in triangle AFC. Therefore, those two triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we conclude two things. The first thing that we conclude that side BD equals to side FC. Side BD equals to side FC according to the rule that corresponding sides in congruent triangles are equal to each other. But according to what is given as the question, BD equals to 5 units. So here BD equals to 5 units. And from this equation 5 equals to BD equals to FC, we will derive that FC is also equals to 5 units. Here FC equals to 5 units. And the second thing that we conclude from the fact that those two triangles can go into each other is that side AD equals to side AF. Repeat again, side AD equals to side AF according to the same rule that corresponding sides in congruent triangles are equal to each other. So if we define side AD as A, here AD equals to A according to our definition, then from this equation A equals to AD equals to AF, we derive that AF also equals to A. AF equals to A. Then we joined points E and F together by a straight line, and we proved that the green triangles can go into the orange triangle. So why those two triangles can go into each other? First of all, we just right now proved that side AD equals to side AF, that is equals to A. Okay, in addition, those two angles, they are both equal to 60 degrees, therefore they are equal to each other. We have already found out that alpha plus beta equals to 60 degrees, therefore those two angles, they are both equal to 60 degrees, therefore they are equal to each other. And finally, side AE is a common side that belongs to both triangles, therefore it equals to itself. So we actually proved that those two triangles can go into each other according to side angle side rule. Here, what I mean is that those two sides and the angle between them in the green triangle can go correspondingly to those two sides and the angle between those two sides in the orange triangle. Therefore, those two triangles can go into each other according to side angle side rule. Okay. Here, triangle ADE congruent to triangle EAEF according to side angle side rule, and from the fact that the green triangle congruent to the orange triangle, we will conclude that DE equals to EF. DE equals to EF according to the rule that corresponding sides in congruent triangles are equal to each other. But according to what is given as the equation, DE equals to X. So we can write here that DE equals to X, and from this equation X equals to DE equals to EF, we will derive that EF is also equals to X. EF equals to X. In the next step I present to you the law of cosines, and we implemented the law of cosines in this triangle, triangle EFC. So what is the law of cosines? The law of cosines is true in any triangle, so we can write down that in any triangle, here triangle ABC could be any triangle. You know that side AB, the length of side AB in triangle ABC equals to A units, side AC equals to B units in its length, side BC equals to C units in its length, and the angle between side AB and side AC is theta. Then, so if this is the data that has been given to us, then the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Then we implemented the law of cosines in this triangle, triangle EFC. Side EF equals to X, side EC equals to 4, and side FC equals to 5. And then get ECF, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees. So, according to the law of cosines, we get that in triangle EFC, x squared equals to 4 squared plus 5 squared, minus 2 times 4 times 5 times cosine 60 degrees. Again, x squared equals to 4 squared plus 5 squared, minus 2 times 4 times 5 times cosine 60 degrees. So x squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40, and cosine 60 degrees is equal to 1/2, so we substituted cosine 60 degrees by 1/2. So in conclusion, we found out that this expression equals to minus 40 times 1/2. So here x squared equals to 16 plus 25 is 41, and here we have minus 40 over 2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20. 41 minus 20 is 21. So in conclusion, we found out that x squared equals to 21. We took a root out of this equation and found out that x equals to the positive square root of 21. Or in terms of numbers, it is equal to 4.58 units. Okay, here x equals to the positive square root of 21 because of the fact that x is a length, it must be a positive number, therefore x equals to either the positive square root of 21, or in terms of numbers, it is equals to 4.58 units. Okay, we finished with the first question. Then I presented to you the second question. In the second question, in the drawing we have a quarter circle. Inside this quarter circle we have a circle and a semicircle that are tangent to each other at this point. The radius of both of them is equal to 2 units. And our mission is to find out the value of the shaded area. So first of all, we know that in any quarter circle, this is the center of the quarter circle. So point O is the center of the quarter circle, this angle, angle BOA or AOB equals to 90 degrees, and here AO equals to BO, and it is the radius of this quarter circle. Okay, so here we know that tangent AO is tangent to this circle at point M. Point M is the point of tendency, and we also have rule number 1 that states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here tangent AB is tangent to this circle at point M. Point M is the point of tendency, and we have the radius OM that is drawn to the point of tendency. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. This is according to rule number 1. We can implement rule number 1 in our drawing because we have the radius PM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent OA with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OA will be perpendicular to the radius MP. So if OA is perpendicular to MP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. In the next step, we did a construction from point P. We draw perpendicular on BO. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BO as N. Again, point N is the touching point of the perpendicular from point P and BO. Okay, so actually we created here quadrilateral NPOM that has 1, 2, 3 right angles inside it, and the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is angle NPM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here, we subtracted 270 degrees from this equation, and found out that the missing angle NPM equals to 360 degrees minus 270 degrees, it is equal to 90 degrees. This angle equals to 90 degrees, so we actually found out that all the angles inside quadrilateral NPOM are right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral NPOM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NPOM, PM must be equal to NO. PM must be equal to NO. But we already found out that PM equals to 2. So we can write that PM equals to 2, and from this equation 2 equals to PM equals to NO, we will derive that NO is also equals to 2. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we get that NP equals to OM. Here NP equals to OM, and if we define NP as X, here NP equals to X according to our definition, then from this equation X equals to NP equals to OM, we will derive that OM is also equals to X. Okay, in the next step we focused on this point. This is the touching point between the circle and the quarter circle, or the point of tendency between the circle and the quarter circle. Actually, the circle and the quarter circle have an internal notch between them at this point, point K. Whenever you have two circular shapes that have an internal notch between them. What is the meaning of internal notch? It means that those two circular shapes are touching each other internally at point K. And whenever you have an internal notch between two circular shapes, then the centers that joins then the straight line that joins their centers together must pass for point K, that is the touching point of the two circular shapes. So here point O is the center of the quarter circle, point P is the point of the circle. Point O is the center of the quarter circle. Point P is the center of the circle. And therefore OP is the straight line that joins their centers together. And according to the rule that I mentioned, this straight line OP must pass for point K. That is the touching point between the circle and the quarter circle. That is to say, OPK is one straight line. Okay, you can write here that OPK is one straight line according to the rule that I mentioned. So if OPK is one straight line, it means that OK is also one straight line. And point O is the center of the quarter circle. Point K is the point of the quarter circle itself. This is exactly the definition of a radius. That is to say, OK is the radius of the quarter circle, and we define the radius of the quarter circle as capital R. So OK, that is the radius of the quarter circle, equals to capital R according to our definition. So here point P is the center of the circle, point K is the point of the circle itself. Therefore PK is the radius of this circle, that is equal to 2 units according to what is given as the question. So in conclusion, we found out that PK is the radius of the circle that is equal to 2 units, while OK is the radius of the quarter circle that is equal to capital R according to our definition. So what is the length of line segment PO? The length of line segment PO or OP is equals to OK minus PK. Again, OK minus PK equals to OP. Repeat again, OP equals to OK minus PK. So OP equals to OK, that is equals to capital R according to our definition, minus PK, that is equal to 2. So in conclusion, we found out that the length of line segment OP equals to capital R minus 2. Then I copied the right triangle OPM in this new page and implemented the Pythagoras theorem on this right triangle, triangle OPM. By PT is the relation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is PO, so the square of the hypotenuse is PO square or OP square. It is the same. So it is equals to the sum of the squares of the perpendiculars. That is to say, it is equals to OM square plus PM square. OP equals to capital R minus 2, therefore OP square is capital R minus 2 square, that is equals to OM square. OM is x, so OM square is x square, plus PM square. PM is 2, so PM square is 2 square, that is 4. So in conclusion, found out that according to equation number 1 and according to Pythagoras theorem, R minus 2 square equals to x square plus 4. Here we open the brackets on this side of equation number 1 and found out that R minus 2 square equals to R square plus 2 square, that is 4, minus 2 times R times 2, that is minus 4R, that is equals to x square plus 4. Here we have 4 on both sides of the equation, so 4 will get cancelled and we left only with x square, that is equals to R square minus 4R according to equation number 1. Then we focused at this point, that is the point of tendency of the circle and the semicircle. The point of tendency of the touching point of the circle and the semicircle. So those two circular shapes have an external arc between them at point P. That is to say, they are touching each other externally at point T. And whenever you have two circular shapes that have internal arc between them, then the straight line that joins their centers together must pass through the touching point or through the point of tendency of those two circular shapes. So here, point P is the center of the circle. Point L is the center of the semicircle. And the straight line that joins their centers together is LP. And according to the rule that I mentioned, this straight line LP that joins their centers together, must pass through point T, that is the touching point between those two circular shapes. In other words, we can say that LTP is one straight line. Okay? LTP is one straight line. So if LTP is one straight line, it means that LP is also a straight line. Okay, LP is a straight line. And here, point L is the center of the semicircle. Point T is the point of the semicircle itself. So LT is the radius of this semicircle that is equal to 2 units according to what is given as the question. Likewise, here point P is the center of the circle. Point T is the point of the circle itself. This is to say, PT is the radius of this circle that is also equal to 2 units. So in conclusion, I found out that LT equals to 2 units and TP also equals to 2 units. Therefore, LP equals to LT plus TP, LP equals to LT plus TP, so LP equals to LT that is 2 plus TP that is also 2. So in conclusion, I found out that LP equals to 2 plus 2, that is 4. If LP equals to 4. Then we found out the length of line segment LN. First of all, point L is the center of the semicircle. Point B is the point on the semicircle itself. That is to say, LB is the radius of the semicircle that is equal to 2 units according to what is given as the question. So what is the length of line segment LN? The length of line segment LN will be equal to BO, that is the radius of the quarter circle, minus BL, minus NO. Again, I'll repeat again, LN equals to BO, that is the radius of the quarter circle, minus BL, that is the radius of the semicircle, minus ON, that is equal to 2. So, in conclusion, we found out that LN equals to BO, that is the radius of the quarter circle, that is equal to capital R according to our definition, minus BL is 2 units, and minus ON that is also 2 units. So in conclusion, we found out that NN equals to capital R minus 2 minus 2 minus 2 minus 2 is minus 4. So in conclusion, we found out that line segment LN equals to capital R minus 4. Then I copied the right triangle LNP in a new page and we implemented the Pythagoras theorem on the right triangle LNP. This is the right triangle LNP. That I copied from the original drawing. We just right now found out that LN equals to capital R minus 4, NP equals to X, and we have already found out that LP equals to 4 units. This is 2 plus 2, that is 4 units. So the hypotenuse LP equals to 4 units, and according to the Pythagoras theorem, in the right triangle LNP, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is LP, therefore the square of the hypotenuse is LP square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to LN square plus NP square. So in conclusion, according to Pythagoras theorem in equation number 2, LP square equals to LN square plus NP square. LP equals to 4, so LP square is 4 squared, that is 16. Plus LN square. LN equals to capital R minus 4, therefore LN square equals to capital R minus 4 square plus NP square. NP equals to X, so NP square equals to X square. So in conclusion, according to equation number 2, we found out that 16 equals to r minus 4 squared plus x squared. Here we open the brackets on this side of the equation and found out that according to equation number 2, 16 equals to r minus 4 squared. R minus 4 squared equals to r squared plus 4 squared, that is 16, minus 2 times r times 4, that is minus r, plus x squared. Here we have 16 on both sides of equation number 2, so 16 will get cancelled. So what is left from equation number 2 after we cancel 16? In this side of the equation, nothing is left. We have 0. On the other side of the equation, we have r squared minus 8r plus x squared. Here we added 8r to this equation, equation number 2. 0 plus 8r is 8r. That is equals to r squared plus x squared. Here we subtracted r squared from this equation, equation number 2, and we found out that according to equation number 2, x squared equals to 8r minus r squared. So this is according to equation number 2, but according to equation number 1, we have already found out that x squared equals to r squared minus 4r. So we have two different expressions for x squared. Therefore, we created equation number 3 that states that x squared according to equation number 1 must equal to x squared according to equation number 2. So x squared according to equation number 1 is r squared minus 4r. And it must be equal to x squared according to equation number 2, that is 8r minus r squared. So in conclusion, according to equation number 3, we found out that r squared minus 4r equals to 8r minus r squared. So here we added r squared to this equation, equation number 3, and we found out that r squared plus r squared is 2r squared minus 4r, that is equals to 8r. Here we added 4r to this equation, equation number 3, and we found out that 2r squared minus 4r plus 4r is 0, and here 8r plus 4r is 12r. So in conclusion, we found out that according to equation number 3, 2r squared equals to 12r. Here we divided this equation, equation number 3 by 2, and we found out that 2r squared over 2 is r squared, and 12r over 2 is 6r. So in conclusion, according to equation number 3, we found out that r squared equals to 6r. Then we subtracted 6r from this equation, equation number 3, and we found out that r squared minus 6r equals to 0. So according to equation number 3, r squared minus 6r equals to 0. We took r as a common factor out of this equation, equation number 3. So what is left from r squared after we took from it r as a common factor? What is left is actually r. And what is left from minus 6r after we took from it r as a common factor? What is left is actually minus 6. So in conclusion, we found out that according to equation number 3, r times r squared equals to 0. So here we have two solutions that are possible for r. The first solution is that r equals to 0, but because of the fact that r is the radius of the quarter circle, it must be a positive number. It can never be equal to 0. So we cancel this solution and left only with the second solution, that r minus 6 equals to 0. Here we added 6 to this equation and we found out that r equals to 6 units. So actually we found out in conclusion that the radius of this quarter circle equals to 6 units. So what is the area of the quarter circle? The area of what is the value of the shaded area? The value of this shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I'll repeat again. The shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. The area of the quarter circle equals to the area of the circle over 4. That is to say, it equals to pi r squared over 4. When the area of the circle equals to pi r squared and r equals to 2, so it is pi 2 squared. And the area of the semicircle equals to the area of the circle over 2, that is pi r squared over 2, and r equals to 2, so it is pi 2 squared over 2. Here, we just right now found out that the radius of the quarter circle, capital R, equals to 6, so r squared is 6 squared, that is 36. So in conclusion, the area of the quarter circle equals to 36 pi over 4, minus the area of the circle, that is pi 2 squared. 2 squared is 4, so 4 times pi is 4 pi. So it is minus 4 pi. That is the area of the circle, minus the area of the semicircle, that is pi 2 square over 2 square is 4, and 4 over 2 is 2. So in conclusion, the area of the semicircle equals to 2 pi. And here 30, so the area of the value of the shaded area equals to 36 over 4 times pi minus 4 pi minus 2 pi. 36 over 4 is 9, so in conclusion, in total this expression equals to 2 pi, that is the area of the quarter circle, minus the area of the circle, that is 4 pi, minus the area of the semicircle, that is 2 pi. So in conclusion, the value of the shaded area equals to the area of the quarter circle, that is 9 pi minus 4 pi, that is the area of the circle. 9 pi minus 4 pi is 5 pi. 5 pi minus the area of the semicircle, that is 2 pi. 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the value of the shaded area equals to either 3 pi square units, or in terms of numbers, it is equals to 9.42 square units. I'm repeating again. The value of this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, thank you very much.